Assalamu alaikum dear students, and welcome to our another lecture of computer networks. In our previous lecture, we have been studying about the network layer, where we discussed in detail about its control plane and data plane. In this lecture, we will be briefly discussing about forwarding and routing, and then we will move on to the routing protocols. Forwarding is related to the router. Movement of a packet from router's input to appropriate router's output is dealt with forwarding, and it is related to the data plane of the network layer. And routing is related to the entire path or route taken by packets from source to the destination. In the context of routing, there are two approaches that are being used in the network control plane. First one is the per router control plane, that is traditional approach, and second one is the logically centralized control. In other words, it is also known as software-defined networking. In per router control plane, here we can see that each router has a separate forwarding table which defines the route or the path of any packet within the router, within a single router, from where the packet enters to the router and to which path the packet will be forwarded from that router. This is per router control plane that is actually related to each and every router in the network. As in case of software-defined networking of the centralized control plane, a remote controller installs forwarding table in the router. This is a separate entity. In case of per router plane, the routing table was being developed and maintained within each router itself. However, in case of software-defined networking, the routing table is being managed, organized, and updated and shared with all routers through a remote controller, that is a centralized remote controller. In case of SDN, the route is managed upon the level of entire topology of the network, and the entire table is installed or downloaded to the all routers of the network. So here we have two options. Which options we are going with this? Are we going to follow the per router control plane? Are we going to use the SDN control plane? In case of larger networks, the software-defined networking control plane is a better option that helps organize the entire network very efficiently. Here we define the routing protocols. What is the goal of routing protocols? For what they are meant for? Routing protocols determine good path. Good path means good in terms of cost, in terms of speed, in terms of congestion. All these parameters actually define how good is the path. And the path itself is a sequence of routers packets traverse from given initial source to the final destination. This is the path that any packet follows to move from source to the destination. So the routing protocols actually determine a good path that is of least cost that is fastest and least congested path from source to destination. Here is a graph abstraction of a sample network, very simple network composed of 6 nodes, and different links and their associated costs are mentioned or shown. Here we can see that the graph G is equal to N, E, whereas N is the set of routers that are named as U, V, W, X, Y, and Z, and the set of the links among in these routers are UV, UX, VX, EW, XW, XY, WY, WZ, and YZ. These are the direct links among all of these routers. Here we can see there is some cost associated between these nodes, and this cost is the direct link cost. For example, CW, Z defines the cost of moving from W to Z. That is, in this case, as I am moving the cursor here, this link has the cost of 5. However, in case of U, Z, we see the cost is infinity. Why it is infinity? It is infinity because the node U and Z are not directly connected. Therefore, we learned that in case the links are directly connected, then we will take the cost of that link. However, in case the links are not directly connected, then we will assume the link cost equal to infinity. Here is a brief description of the classification of routing algorithms. The global routing algorithms, where all routers have complete topology and link cost information that we earlier discussed, that software-defined networks are the link state algorithms that are global routing algorithms. And the second category becomes the decentralized routing algorithms, where iterative process of computation, exchange of information with neighbors takes place. The distance vector algorithms are the decentralized algorithms. Another category becomes the static algorithms, that the routes change slowly over time. However, the fourth category of the routing algorithms is the dynamic algorithms, where routes change more quickly. Periodic updates are in response to link cost changes. Here's the summary of our entire chapter. Next, we move on to our core algorithm, that is Dijiksra algorithm. This is link state algorithm. And as you see in our previous slide, in this slide, distance vector algorithm, we will discuss it in our next lectures. The Bellman-Ford is the core algorithm of the distance vector algorithms. So we come to the Dijikra's link state routing algorithm. It is a core algorithm used by link state router protocols to compute the shortest path from source router to all other routers in the network. It is most commonly used by open shortest path protocols. This algorithm ensures that packets are forwarding along the least cost path. As we discussed earlier, that the objective of the routing protocols is to find out a good path. And we also discussed in our previous slides what is good. Good means which is of least cost, which is of least congestion, which is fastest, that was defined as good. So the objective of Dijiksra algorithm is to ensure that packets are forwarding along the least cost path, improving efficiency, reliability, and overall network performance. In link state routing algorithms such as Dijiksra algorithm, each router independently builds a complete map of network topology. The map is created using information shared by all routers in the form of link state advertisements. Once the topology is known, Dijikra's algorithm is applied to calculate the shortest path tree with the router itself as the root. From this tree, the router constructs its routing table. Dijikra's link state routing algorithm is centralized. It has network topology, link cost known to all nodes, that is established via link state. The cost of each link. All nodes have the same information. Dijikra's link state routing algorithm computes least cost paths from one node to all other nodes, and at the end it establishes or develops a forwarding table for that node. Dijikra's link state routing algorithm is iterative. After k iterations, it knows the least cost path to k destinations. Here in this side, we can see notations used in Dijikra's link state algorithms. C, x, y denotes that there is a direct link between nodes x to y, and if there is no direct link, then as we discussed earlier, we will denote the cost as infinity. Otherwise, we will mention the link cost of that link. dV denotes the current estimate of cost of least cost path from source to destination node V, whereas PV denotes the predecessor node along path from source to V. However, the N prime defines the set of nodes whose least cost path is definitely known. Here we see the notations C, x, y. It defines that the x is the source node and the y is the destination node, and C represents the cost of moving from x to y. If there is any direct link between x and y node, then we will get a cost of that link. But in case there is no direct link between x and y nodes, then we will be initially considering the cost equal to infinity. dV denotes the current estimate of the cost of least cost path from source to destination V, and the PV denotes the predecessor node along the path from source to V, whereas N prime is the set of the nodes whose least cost path is definitely known. This is algorithm. It has initially two phases. First phase is initialization, and the second is the major phase is the loop phase. In initialization phase, we see at line number 2 that N prime is initially composed of only set U. It means that we are computing the forwarding table for node U. At first, we are considering that our source node is U and destination node is also U. For all nodes V is adjacent to U. Here V denotes all other nodes of the network that are not U. If V is adjacent to U, then dV is equal to C U, V. It means that the cost of moving from U, V in case U and V are directly connected. Else, cost of dV means the cost required to reach up to V naught. Here in the brackets V is shown that represents that the V is the destination node, and if C, U and V are not directly connected, the cost will be considered equivalent to infinity. Comes the second phase of the Dijiksra algorithm, that is related to the loop. In this case, find W naught and N prime. We know the N prime is the set of all nodes whose least cost path is obviously known, definitely known. Now we are going to find any node that is W that is not already in N prime, and its price, its D, value of D is minimum. As we find out the node W, we will include this node to the set N prime that is composed of the least cost path nodes. Afterwards, as shown at line 11, we will update the EV of all nodes that are adjacent to W by using following equation. As the equation dV is equal to minimum of dV, dW plus C W, V. We will have detailed discussion through implementation example in the next slides. Here is an example where we can see there are 6 nodes. There are edges among nodes, and there is a sum associated cost of each link. We will be starting from U. Here, N prime denotes that U is the source and U is the destination. And V, it means we are moving from U to node V. dW means we are moving from U to W. Here, we are moving from U to X. We are moving from U to Y, and so on. Whereas PV states that what is the predecessor node of the node V, which one is the predecessor of node W, which one is the predecessor of node X, and so on. Here we see that in case of moving from U to V, we have direct link, so the dV becomes U, that is mentioned here. And which one is the predecessor of V, that is U. So we have written U, U. In case of W, cost is 5 and the predecessor is U. In case of X, cost is 1 and the predecessor is U. Whereas in case of Y and Z, as U is not directly connected to node Y and Z, therefore their cost is mentioned as infinity. Here we have to find out the minimum, as we saw in our previous slide. So as we can see that 1 is the minimum cost, therefore we will pick X and move this X to the set N prime. Now we will find out the adjacent nodes of X and move forward. Here we can see that V, W, and Y are the adjacent nodes of X. So we will recompute the cost using this equation. We can see that when we put the values to find out the value of dV, we get the value, the cost equivalent to. In case of dW, we find out a new cost that is 4. In case of dy, we find out another new cost that is 2. Whereas in our previous iteration, it was infinity. So we will update these costs in the next slide. Here we can see that we have entered new costs. Cost of dV remains the same. The cost of dW is updated up to 4x, and the cost of dy is now come 2 instead of infinity. Now we will find out again the minimum cost. Now here we can see 2, u and the 2, x. These both have the minimum cost. We will pick one of them and move the next step. Here we can see that the y is picked and we moved on the next step to update the values again. Now we will see which nodes are associated or directly linked with y. Now we see that w and z are directly connected with this node y. So we will recompute the cost of w and z, the cost of the destinations w and z. When we put on the values in the equations, we again get another cost of dw, that is 3, and the cost of z becomes 4 now. That was infinity in our earlier transaction. Now we will again find out the least cost, and it becomes v. Therefore, v now comes to the set and prime. Next we move on and we will check which node is now adjacent to v. And we can see u is adjacent to v. Therefore, we will find out the cost of dw, the cost of reaching w again, and we see that we get the cost of 3 that is similar as we got the earlier. Now we will have a look and see which cost is now smaller. Now we will see that the cost of w is smaller. Then we will pick this w and move this w to our set of n prime. Here we can see that right now the set of n prime becomes u, x, y, v and w. Now we move on and we will get the price, the cost of reaching dz, because we are starting from w, then we have to traverse the node that is adjacent to w, it is z. So we will calculate the cost of z, and it again we get the minimum cost of these two options is 4. And at the end we will pick the node z as well and get it the set and prime. Here is the summary. As we have been moving across the whole example. One by one, we have been moving the nodes to our set and prime, for which we have a definitely known cost. Here comes the forwarding table and resulting least cost path tree from u. Remember, each node of this sample network has its own routing or forwarding table that defines that from that source node to any other node of that network, how the packet will be moving on. Here is the summary. We can see that from u to node v, we will be traversing this path, that is u, v. From u to x, we will be using this link x. From u to y, we will be again using the link ux. Now, here is the question. When we want to reach up to x, y, w, and z, our next destination remains the same. It means there is another path with x. that defines how to reach Y, how to reach W, how to reach Z, considering only the one parameter, that is least cost. It means when the kit is to move from U to Z, at first we'll move from U to X, and then X will define the forwarding table at X will guide where to move next. And in this case, the final route path is defined. And here we summarize that Dijiksra's algorithm, that is a core routing algorithm, a link state algorithm, works on the condition on the cost of the links. If the links are directly connected with the source node, then the cost is taken up. And other case, if there is no link between source to destination, no direct link between source to destination, the cost is considered initially infinity. Then following the algorithm steps, we compute the cost of each node, and each node of the network has its own forwarding table. And at the end, we get a loop or a path or a route that is least cost path from source to destination. Dear students, with this discussion, we come to the end of our lecture. Thank you so much.